All right, guys, question number 2, AP Physics 1 2024 actual exam. Uh, a student hangs a spring of unknown spring constant K vertically by attaching one end to a stem. The other end of the spring has a small loop from which small cylinders can be hung. In addition to the spring, the student has access only to a variety of cylinders of unknown mass, a stopwatch, and a digital scale. There's an experimental procedure the student could use to determine a spring constant K of the spring. Remember, the cylinders are of unknown masses, right? Okay. In the following table, list the quantities that would be measured only using only the provided equipment in your experiment. Define a symbol to represent each quantity. Space below the table. Uh, Describe the overall procedure. Provide enough details so that a student could replicate. Include any steps necessary to reduce experimental uncertainty as needed. Use the symbols defined on the table. If needed, you may include a symbol diagram of the setup with your procedure. Okay, so the first thing which is coming in my mind is can we do kx naught is equal to mg? Because when we do kx naught equal to mg, we are basically implying that when the spring stretches and it will ultimately come to an equilibrium. But the only problem is we don't know the value of x naught and neither we have a scale. We can measure mass from the digital scale, but we cannot measure x naught. So that will not work. What's the other thing which comes in our mind using a spring mass? SHM, I think. And if we remember, spring mass system provides performs an SHM with the time period of 2 pi square root m over k. I can measure time using the stopwatch time period. I can measure the mass using the digital scale, and then I can find the value of k, right? So I'm going to say that the quantity to be measured, I think capital T is the usual representation of the time period. And the other thing was, what was that? M. M is the mass of the weight. So M is the mass of the cylinders, and T is the period of the SHM. Remember that it will not be an ideal SHM because there will be a damping. Damping as in, since there is an air resistance, it will not just keep performing to and fro oscillations forever. Obviously, it will stop after some oscillations, and that's why we need to take multiple, readings so that we can average this out. So, what will be the procedure? The procedure will be first measure the mass of one cylinder, attach it to the hole at the bottom of spring. The third one is stretch the cylinder downwards uh, uh, by some distance, or if you want to be more specific, maybe 3 centimeter, I think, or stretch the cylinder downward by 2 to 4 centimeter and uh, hold at this position, hold here, and uh, get ready to start the stop clock or a stopwatch. Release the mass and start the stop clock. Measure the time it takes for, let's say, four oscillations. What do I mean by four oscillations? It means that it was initially here and we have stretched it till this point. So it'll go up, down. This is one oscillation, two, three, four. Four oscillations. Then divide the total time by 4 to get the time period for this particular scenario. So this becomes your one set. Um, so step 7 will be repeat 1 to 6 for a cylinder of, or for cylinders of at least maybe 4 different cylinders, for 4 different cylinders. So that way we will minimize our error, right? So if we do this, we will have 4 sets now. We will have one set of, let's say, M1 T1, then M2 T2, then M3 T3, then M4 T4. We will have these 4 sets, and perhaps we can add, I think, another step here. Don't you think that we can make it a step 8? And step 7, we can say that the single measurement, as in the total time which we have taken by 4 oscillations, that also we can measure maybe 3 or 4 times. So measure this maybe 2 to 4 times to eliminate error. And then repeat 1 to 7 for 4 different cylinders. Uh, and then in step number 9, we can show them the calculation. That for the calculation point of view, we already have t is equal to 2 pi square root m over k. So you're going to square 4 pi square m over k. We are going to cross multiply. So k will be equal to 4 pi square m over t square. So this is going to be the spring constant. So all we have to do is plug in this m1 t1 to get k1, k2, k3, k4. Step 10 will be get k1, or obtain rather, obtain k1, k2, k3, k4 from uh, from from those 4 sets. In fact, measure this 2 to 4 times and take its average. It will make more sense, like take its average value. Take its average value. Okay, obtain k1, k2, k3, k4 from those 4 sets, and then k observed will be the average value of all this. So k1, k2, k3 plus k4 divided by 4. That will be the entire procedure. Okay. The next question is, indicate the quantities that could be plotted to produce a linear graph whose slope can be used to measure or to determine the spring constant K. Okay, linear graph, right? Yeah, I think we have it. For the linear graph, I think I'm gonna borrow this and redecorate this a little bit. So let me do that. Okay. Now, if we need the linear graph, let's stop here. In fact, yeah, let's multiply both sides with k. So kt square is equal to 4 pi square m. Let's flip the omelet. So in fact, yeah, actually, let's flip it. So 4 pi square m is equal to kt square. So don't you think if this entire thing is y and this is x, so the slope is going to be k. That's what they need, right? So the vertical axis is going to be 4 pi square m, and the horizontal axis is going to be the square of the time period, and that's how we are going to find it. Briefly describe how, so then I think if they are finding using the graph, there is no need to obtain, well, to do step 10, is it? Because we are ultimately using the graph to find that out. Briefly describe how the slope of the graph would be analyzed to determine the spring constant K of the spring. How the slope of the graph would be analyzed. I think they're asking about the analysis. Perhaps it will make more sense if I only plot, okay, let me explain what I'm trying to say. If I rearrange this, m is equal to k over 4 pi square t square. This can also be a graph, and now I think we can answer the part 2 as well, because otherwise part 2 is like describe how will you analyze. We don't analyze it, right? If we graph between 4 pi square m and t square, then the slope is the k. But now let's say if I graph between m and t square, which I think some of you might have done, then we can analyze, because now the slope can also be used to determine the spring constant, but that will not be given right away, because now we have to analyze it. What we are going to do is we are going to say that k is nothing but the slope, whatever we are getting, and that should be multiplied with 4 pi square. That is going to be the analysis, the so-called analysis. So that's how we do part 2. Okay. The next one talks about in a different experiment. Now the student, okay, in a different experiment, the student attaches one end of a spring to a force sensor that is attached to a wall. The other end of the string is attached to a cart with a mass of 0.25 kilograms. So this is 0.25 kilograms. Student places a motion detector to the right of the cart, uh, okay, and pulls the cart to the right a small distance so that the spring is straight. The student releases the cart from the wrist, and the car spring system oscillates. The following graph shows the velocity of the cart and the force exerted by the cart as a function of time. Okay, all right. Using the data and in the velocity time graph, calculate the change in kinetic energy of the cart from 0.5 to 2. Show the step. Okay, so well, at 0.5 we have a speed of what was that? I think 0.5 at 0.5, 0.3, and at 2 seconds the speed is 0. So the change of kinetic energy is half, ke final minus ke initial. Final is 0 and initial is half mv square, and the mass was given as 0.25 and v is 0.3 square. So that's where my calculator comes in. So 0.25 divided by 2 multiplied with 0.3 square is minus 0.01125 joules. That will be the change of kinetic energy. Okay. The next one is using the force time graph, estimate the change in the momentum, estimate the change in the momentum of the cart from 0.5 to 2.5, and briefly explain how you arrived at your estimation. So I think I'm going to borrow the force versus time curve, because I know that, okay, what I want to say is I know that f delta t is delta p. So the area under the force versus time curve is the change in the momentum, which is what they need, right? Change in momentum. So let's find the approximate area between 0.5, which is this one, and 2.5, which is, I believe, this one, right? And well, the way I see it, between 0.5 and 2.5, they're asking the change in the momentum. Don't you think that this is like a symmetric curve which will eventually be cancelled by this much? Because the bottom area will be considered negative and this top area will be considered positive. So 0.5 to 1.5 and then 1.5 to 2.5. I think the change of the momentum should be 0, because the area under the curve, which is the equal negative area and the equal positive area, basically cancels each other. Right, so this should be 0, and we have already explained. And okay, do the data from the velocity time graph confirm your estimation from part C2? Oh, you mean they mean the change in the momentum, is it? Okay. I think, yeah, it does. It does definitely. Because at 0.5, the velocity, and at 2.5, whatever the velocity is, it's same. Because I'm not interested in speed, by the way, because a change in momentum is nothing but m times change of v. And since change of v from 0.5 to 2.5 is 0, because that is same. So definitely it confirms my selection of C2. So I'm just gonna put my solution here. So my answer is yes, it confirms definitely from the velocity time graph, and C2 and C3 are, C2 and the graph velocity time graph are aligned. Okay. Right, that's it for question number 2. Any questions, post it down in the comment section and I'll see you in the next video.